In this discussion, we want to look at another physical system that has two-state observables, and that is polarization of light. Now recall, classically, polarized light, which you studied in the optics course, is defined by the direction of the oscillation of the electric field component of electromagnetic wave. And also recall that the intensity of light is proportional to the electric field squared, the magnitude of the electric field squared. So there's definitely a connection there. And again, the connection is, well, how is it a two-state observable? Well, we remember what we want to do is we want to go from intensities down to probabilities. So if we take a light source, say coming up to a polarizer, a linear polarizer, the classical description is that, well, certain amount of light passes through, the intensity drops or stays the same, depending, and the intensity drops. But now what we want to think about is we want to transfer that to single photon cases. So in single photon cases, then, we want to say a single photon comes up to the polarizer. Now the question is, does it pass or does it not? And that's a probability question. So the way we map this now, just like we did earlier, is, if you recall Malice's law, that the intensity is, if we have, say, begin with a linear polarized light source that has intensity I0, and say the polarizer is at an angle theta with respect to that state, the intensity is cut down by a factor of cosine squared. But again, when we convert that to probability, remember there's a definite mapping from probability to intensity as we increase the number of particles. We see that the probability of transmission is simply cosine squared theta with the same setup. So that's essentially how we want to think about it. And so, to do this now, the two states are essentially, we could think of it as transmission, not transmission. Those are the observables. They could also be created in a way with what's called a polarizing beam splitter, where it can go one way or the other. But it is only two possibilities of measurement. And again, here we'll just stick with measurement, not measurement. Those are mutually exclusive outcomes. So that gives us a two-state observable. And what we want to do is construct a basis within the Hilbert space for this, and it's going to be analog exactly to what we did with spin. So we'll just fix a direction. We could say the xy axis perpendicular to the axis of transmission, because remember the polarization lies in the perpendicular plane to the axis of transmission. And what we want to do is just fix two kets. Those are our basis kets, and we're going to call them H and V. What that means is horizontal and vertical. So we can represent that if we want. Let's zoom in here for a minute, take a big look here. So let's say we have, so this is we can think of this, first of all, as the physical space. This is the nice thing about polarization. There's a one-to-one mapping between physical space and Hilbert space. But actually, we will be talking about Hilbert space. That's what we're doing. So we call this horizontal in this direction. And then this direction we'll call this vertical. And again, these are unit vectors, and H and V form an orthonormal basis, just like we did for spin. Okay. So this, again, now any polarization in this plane, again, we can think of it as the physical, in this case, we can think of it as the physical plane perpendicular to the direction of travel of the photon. And that doesn't work for spin, but we'll come back to that. But we can define now any kind of polarization in this two-dimensional plane that's perpendicular to the direction of travel. So there's a one-to-one mapping, which makes this nice. So we can think of the most generally one, it's just the general case is just going to be cosine H plus sine V. And that would be the case where we have some state vector that's at some angle. That's supposed to be a state vector there. Some angle to the horizontal, and that's the angle theta. I'm trying to make that very small there. And again, notice that in our column vector form, it's going to be cosine theta sine theta. So you would think this is the most general case you can have. There is one small addition, though. Well, it's not a small addition, but remember, our states can be complex now. And I'm not going to get into the details here because it would take us too long to go into it, but there will be notes supplied. That the most general form is by putting a phase factor here. Again, here, there's a convention to put it there. Now, there's a reason why where it's on one term and not the other. It's because otherwise you can always write it as a global phase factor, which you can ignore. But this two-parameter ket now, theta and phi, is really kind of the most general form for a polarization state. And we'll see how this factor comes into play later, but we're not going to really emphasize that in this course at this point. So let's just take a look at how this works now. So what we're going to do is say we have a photon in a state, we'll call it theta for now, that's referring to the angle. And we want to know if it comes up to a polarizer that's in the h direction, what's the probability that it's going to pass? And that's a natural question to ask in quantum mechanics. What's the probability that the photon is transmitted? Well, recall, we'll go back to our Born probability rule. The way we do that is we take the bra of what we want to find, which is h in this case, acting on the state it is in. So it's going to look like this. And now we see, so it's h on the state theta, but theta, again, we're writing it back out. And we see that when we slam in the h, it will be h on h and h on v. But remember, these are an orthonormal pair. So that means that this term goes to 0, and this goes to 1. And what we're left with is just cosine squared theta, which is what we said. That's Malice's law. So this is how we think of Malice's law in quantum mechanics. And again, it's very close. It's very close to the classical one, because remember, in the classical one we talked about the component of the E field in this perpendicular plane. Now we're just calling that the state vector. So there is a very much there's a nice natural translation from there to there. But again, I will remind you that that doesn't always happen. In the spin case, remember, we had x, y, and z all mapped into this way, so we can't physically think of the Hilbert space mapped directly into physical space. Okay, let's do another example here, and this will get us to the next thing we want to talk about. But let's consider a photon in what I'm going to call the pi over 4 state for the moment. That means that the angle theta is set to pi over 4. And again, it's going to be incidental polarizer in the h direction. We can write this as follows, and we're going to define this. This is a convention again. We're going to call this P for plus. I could write plus, but we don't want to confuse that with the spin cases. But that means we rotated by plus 45 degrees, or pi over 4. So going back to the original ket, and in this case there's no complex phase factors. So we have cosine pi over 4, sine pi over 4. But remember, those are each 1 over square root of 2. So we simply have this ket vector here with a 1 over square root of 2 factored out. And we've played with kets like this in your homework. So we should be a little familiar with this. But again, the important thing to notice is that if we act on h or if we act on v and use the Born probability rule, the probability, should be clear, to measure h or v is going to be a half. Now here's where the importance comes in, because this is it's an arbitrary basis, or ket, if you will, this p, but it's important to note that if we have perfect knowledge that it is in the state p, which is what we're saying here, we're saying, oh, we know it's in the state p, because the probability is a half to measure an h or v, we have no idea whatsoever whether that photon is h or v before we measure it. We only have that information after we measure it. Before we measure it, half and half means you have no knowledge whatsoever. It's just completely, could be, yeah. So that's what we mean by that. The significance of that will come up in a minute. But let's look at another ket which I can define, which I'm going to call m for minus, which is just going to be rotating it by 45 degrees. So again, maybe we should draw a picture of this real quick. So we're going to have, I'll put the original h and v here. So here is h, here is v. But now we want to write, I'm going to use two different colors here. Well, no, we don't have to, but the plus 45 degrees, this is going to be the p state. And notice it splits right in half of the two. It's of unit length, even though I didn't draw it perfectly. And the m is like this. So this is a new basis. Notice p and m are orthonormal themselves, but it's rotated by 45 degrees. So since we can talk about a general ket vector, again, it's the same Hilbert space, we can either represent it in the VH bases or the PM bases. We have that freedom to choose. But of course, you really want to choose the basis in which you're going to measure. So if you're going to measure, like, if you want to know what the probability is in M, then it's more natural to use the PM bases. But you don't absolutely have to. Now, again, these form an orthonormal base. And here's a definition. So we consider the two bases of H and V, that's one orthonormal base, and P and M, that's another orthonormal base. These two bases are what we call complementary. Again, it goes back to the statement up here that if you know one, you can only have perfect knowledge in one of those two bases at a single instance of time. If you know it in one, you have no idea what it is in the other. That's important. And this also occurs in the spin case as well. So X and Z and Y, they're all mutually complementary, I would say. Now, you remember in spin we had three complementary bases measuring the Z direction, the X direction, and the Y direction. Likewise here, polarization, there are three complementary bases. The third one is, you may try to guess, but go back to our discussion of classical polarization. Remember, there was another type of polarized light, which was circular polarization. And the bases here takes the following form, where notice now we have an I involved here. So now these, you can quickly check that these two are orthogonal to each other, they're normalized. And the other thing to check is that for example, if I know exactly what it is in the H bases, say I start with an H, I have no idea what it is in the R and vice versa. So it's definitely complementary to the HV bases. It may take a little bit of effort, it doesn't take much, to show that R and L are complementary to the PM bases. So they're all mutually complementary. Again, if you know what it is in the R, you have no idea what it is in the PM bases. And again, there's a little bit of work just to write this R by using these forms in the PM bases. We'll leave that for exercise for you to do. Now, okay, so this is just a quick introduction to the polarization case. And again, notice that the thing to notice here is that there's this it's almost identical to what we did in the spin case, which is we're just changing the labels. All right? So here is what we just defined, our HV bases, H and V, and we use these column vectors. And now, remember the P was H plus V, so we add these two components and so on. Probably go back and check that, if that doesn't seem right. But I've also added here the spin half bases. So this is the Z bases, we have plus and minus. In the Z direction, we have plus and minus in the X direction, and plus and minus in the Y direction. This is how we define those kets. And so there's this one-to-one mapping, or this isomorphic, if you will, that the polarization and spin half Hilbert spaces are isomorphic. So they're the same. That's what we mean. Then the mathematics is the same in the Hilbert space of those two. Does that mean that they're the same? That everything's the same between them? And the answer is no. Now, here's where it gets interesting. But so the Hilbert space structure is identical for polarization and spin 1/2. However, it's when you map it back to the physical space that there's a difference. So the Hilbert space structure is isomorphic, but the mapping to the physical space is different. So again, go back to spin, and remember the complementary bases, like Z and X, for example. Z and X are in physical space are separated by pi over 2 radians. And so is X and Y, so is Y and Z. They're all pi over 2. To get from one base to the other, you rotate by pi over 2, 90 degrees. So what that does is that it allows us to write the most general spin ket, which we may have done before, but here it is again. Most general spin one is going to look like this. Again, and notice when we find the probability, say, to find it in one of these case A and plus, we get the Malice's law, except for the theta over 2. Not theta, but theta over 2. And again, to remind you again, the most general polarization state is like this, where it's just theta as opposed to theta over 2. And so the Malice's law is cosine squared theta. Now you might think that, oh, okay, well that's not a big deal, that's not a big difference. It turns out that this is actually extremely significant, and the details of which I can't go into, but I will just highlight the significance of this. But first of all, notice that the photon polarization is 2 pi symmetric, meaning that if I take theta and rotate it by 2 pi, you get the same state back, and the polarization remains the same. Sorry, the probability remains the same. Well, and the polarization. However, notice the spin state. The spin state, if you rotate by 2 pi, cosine doesn't come back. You get an overall minus sign because it's be 2 pi divided by 2 is pi, and if you rotate by pi, you change the signs. So spin is 4 pi symmetric. You have to rotate twice to get back to the same state for a spin 1/2 object. And again, the corresponding probabilities are there. Now, here's where this gets interesting, is that, well, there are actually systems that are 4 pi symmetric, and there are some nice little parlor tricks you can do. One's called, if you look, search for Dirac belt trick, you'll find a nice little way. You need a friend to show something that's 4 pi symmetric. However, just to kind of fill this in, don't worry that this is not going to be part of the curriculum here, but I do want to say that this difference here is extremely significant, and it boils down to the fact that spin 1/2 objects are spin 1/2, meaning what we call fermions, and photons are bosons. It's a spin 1 object, actually, and with one of the components of the polarization being squelched because it's traveling at the speed of light. But the fundamental difference between the way fermions, which make up matter, essentially, remember quarks, electrons, make up our matter, which is solid and takes up physical space, that existence is different than for bosons, like photons, which form fields, if you will, but they can be all on top of each other. And if you may have heard Bose-Einstein condensates, where you can put a bunch of bosons in the same place, in the same quantum state, you can't do that with fermions. So that's part of the reason why matter takes up space. And if everything were made of bosons, then it would not take up as much space. The Pauli exclusion principle stems from this, and a lot of the whole structure of chemistry and the structure of matter and our universe really does boil down to this kind of tiny little difference in a way. Actually, there's more to say about that, but it requires quantum field theory. And it is a bit of a challenge to actually describe that in an easy way. But it's reflected in this difference here. So that the difference here does have implications for the large-scale structure of our universe. So it's not just a little mathematical trick. It's actually behind a lot of what we see in our universe. Save that for another class.